So now that we're dealing with exponentials, we can talk about two distinct rates of change. So what we're used to, or at least with linear functions, was something that changed consistently as we incremented our independent variable. In this case, let's call it x. So for every change in x, we get a consistent change in y, which is given by the slope. So the average rate of change would be represented by the slope, which is approximately the change in y over the change in x. Now I say approximately because for something like a quadratic, that doesn't stay the same all the time. But for a linear graph, it's that average rate of change is exactly delta y over delta x, as long as it's a perfectly linear slope or perfectly linear graph. Now, for an exponential function, you end up getting this constant relative rate of change. So say, for example, 5% increase every year, or 9% decrease every generation. So there's a constant relative rate of change for an exponential function. Now, the relative rate of change would be given by your slope divided by the initial value y. So if I were to write this out, it would be approximately, let's say, my delta y divided by my delta x, because that's my slope right here. And then I would divide that by my initial y value. Now I want you to work through some of the math to show that I can go from that delta y over delta x all over the initial value of y to this version right here, because this is that say 5% version or 9% version, or my delta y over y compared to delta x. It's the relative change in y relative compared to its initial value as I change my x. So my relative rate of change is going to be given by this equation, and for an exponential function, for a consistent delta x, you're going to get a consistent relative rate of change. So to explore how that behaves, I thought I'd look at, say, an investment scenario where you have one investment where, say, you get $10 per day. So you start with $100, $110, $120, $130. That would give you this straight line right here. So investment scenario A. And then you can consider another investment scenario, say B, where every day you would get a 1% return on investment. And so if you start with $100, you get a 101 the next day, but on day 2 you would get well, you'd start with your 101 and then add 1% of 101 onto that. Now initially, obviously that linear one is going to be winning out. It's way better to go with the $10 a day early on than the 1% a day, because at first that 1% is only $1. But at some point, which seems to be about a year later, it ends up that the exponential function takes over, and you get much more return when you have that consistent relative rate of change compared to the linear one. Now that's going to be true, actually, exponential functions compared to linear or other power functions. It's always, in the long term, going to win out. It's always going to dominate as you go to larger and larger values of x. Now, but you'll see that if I were to look at the slope of the exponential function early on, that would have started, say, somewhat shallow right there, certainly shallower than the initial linear function. But then by the end, oh, that didn't turn out into a line. Let me try that again. By the end, you get this much sharper, let's move that over. There we go. Kind of like that. Anyways, you get what I'm trying to get at. It's much steeper later on compared to the linear function. So it starts growing slowly and then it ends up growing quickly. Now, to get a sense of relative rates and average rates of change, I'd like you to take a minute and go through these two questions. What I'm looking for you to do, we know that the 1% per day might be given by a formula like this. I have my initial value, which was $100, and then I'm increasing by 1% per day. Now, if I change my delta x, that's going to change my delta y over y if I have a consistent relative rate of change. So I want you to find the relative rate of change per year by using that formula and building a new table. And so your table of values, if you have a particular year, then you'd find out what your investment is. And so you're looking at an equation that's going to look like I is 100 to the something to the power of, in this case, y is my independent variable because I'm looking at years. So we know what the value is at 0. My investment is 100. I want you to get the values for year 1 and year 2 using the fact that 1 year is 365.24 days. Then once you're done that, I'd like you to calculate relative rates of change and also look at how the average rate of change differs when I consider at different points. So that was like looking at the slopes as I was showing before. And then also repeat it with a relative rate of change. And you should see that the average rate of change and the relative rate of change for an exponential function behave quite differently.